Today, we're cracking open one of the oldest debates in computer science to uncover a performance secret that, honestly, most textbooks just gloss over. It's the classic showdown, array versus linked list.
Yeah, I know what you're thinking. You probably learned about these in your first programming class and figured, okay, got it, case closed. But what if that simple story of trade-offs is hiding a much bigger, much more interesting truth about how your computer actually works?
All right, so before we get to that big secret, let's do a quick refresher. Let's talk about the classic showdown everyone learns in school.
So in one corner, you've got the array. It's neat, it's orderly, a solid block of elements all sitting right next to each other in memory. Super predictable. And in the other corner, you have the linked list, a chain of nodes, where each one holds a piece of data and then points to the next node, and these things can be scattered all over your computer's memory.
And this table, this is the story we all learn. An array gives you instant, what we call O of 1 access to any element, as long as you know its index. But want to insert something at the beginning? Ugh, that's slow. O of n, because you got to shift everything down. A linked list is pretty much the opposite. Inserting at the start, super fast, O of 1. But if you want to get to an element in the middle, you have to walk the entire chain from the beginning. That's an O of n trip that gets slower and slower the bigger your lists get.
So far, so good, right? Seems simple enough. But this is where our real story begins, with a performance puzzle that kind of throws that whole neat little table into question.
Just think about it for a second. If you have to scan through a list to find something, and you don't already know its index, the big O notation is O of n for both an array and a linked list. So, they should be equally slow, right? Well, let me tell you, in the real world, they're not. Not even close.
This quote from a developer discussion just nails it. In practice, an array is often dramatically faster, even when it's doing the exact same O of n scan. So what in the world is going on? Why doesn't Big O tell us the whole story here?
Well, to solve this puzzle, we have to pop the hood and take a look at how your computer's memory is actually organized, and how the CPU gets stuff from it. So here's the most important thing to get. Your computer's main memory, the RAM, is basically just one giant long straight road with billions of numbered houses. Every single piece of data lives at one of these addresses.
Now, because an array's elements are all stored together, contiguously, they live in a block of neighboring houses on this street. For the CPU, reading through an array is like reading down a single page in a book. It's predictable, it's efficient. This idea is called spatial locality.
Okay, so to speed things up, the CPU doesn't run all the way to the main memory library every single time it needs something. No way. It has this tiny, incredibly fast notepad right on its desk. We call this the CPU cache. And getting something from this cache is magnitudes faster than going all the way out to the RAM library.
And here it is. This is the secret. When the CPU needs some data from one of those houses in memory, it doesn't just grab that one piece. It's smart. It grabs the entire neighborhood of data around it and sticks it on that super fast notepad, assuming it's going to need it soon. For an array, this is a total jackpot. The CPU asks for the first element, and it gets the next, 10 or 20 for free, already sitting in its ultra-fast cache.
But for a linked list, this is an absolute nightmare scenario. Its nodes can be scattered all over that memory street. The CPU fetches one node, but the next one could be in a completely different zip code. It can't prefetch anything useful. Each jump from one node to the next can cause what's called a cache miss, forcing a slow, painful trip all the way back to the main memory library.
This quote just sums it up perfectly. Every time a linked list has to follow a pointer, it's a potential performance disaster for the CPU cache. The cache just takes a battering, constantly having to look up these scattered addresses. That's what kills the performance, even if the number of steps is technically the same O of n.
And listen, this is not just theory. The real-world numbers are absolutely staggering. Look at this benchmark. When we access a huge matrix row by row, the cache-friendly way, where everything is next to each other, we're processing almost 66 billion items a second. But when we access it column by column, jumping all over memory, that speed absolutely plummets to just 2.6 billion. That is over 25 times slower for the exact same number of operations.
Okay, so now that we know the secret, it's all about the cache. How do we actually use this knowledge? Let's build a practical playbook.
The choice becomes so much clearer now, doesn't it? You should use an array list, or anything built on a contiguous array, for pretty much any general-purpose list, especially for read-heavy operations or random access. Its cache friendliness should make it your default. You save the linked list for very specific cases,
Like when you are absolutely positively acting like a queue or a stack, constantly adding and removing from the ends, and you almost never need to search the meta.
And here's a perfect real-world example from a Spring Boot app. The product catalog, stored in an array list. It gets loaded once and then read thousands of times. Perfect for fast, cache-friendly lookups. But the queue of incoming orders, that's a linked list. Orders are always added to the end and processed from the front. A classic first-in, first-out queue. That's exactly where a linked list really shines.
Now, knowing this secret about the cache, it really opens up a whole new world of more advanced data structures.
So what happens if you need both? I mean, what if you need the fast searching of an ordered structure, but you also need fast insertions and deletions without having to shift around massive chunks of memory?
Well, this is where incredible structures like a skip list come into play. It is a brilliant idea. It uses randomness to build multiple layers of linked lists on top of each other. The bottom layer connects every single item, but the upper layers act as express lanes, letting you skip over huge sections of the list. It's literally like having local and express subway lines to get across town way, way faster.
So the next time you're about to choose a data structure, don't just think about big O notation. Think about the memory. Think about the cache. Think about how the hardware actually wants to work. Because, understanding this secret is what separates the good programmers from the truly great ones. Thanks for diving into this with me.